Hello, this is Dr. Coroner, and this is a pre-lecture video to the first half of Chapter 1. Before we begin our first video, here's a little bit of information about the purpose of these videos. These videos are meant to be a way to help you prepare for lecture. You may find reading the book is all you need to do to prepare for class, but if you need a little bit more help, or if you need a little bit more instruction, these videos provide you an opportunity to watch whenever you're free, at whatever speed you wish. You can speed them up, slow them down. You can incorporate these videos before you read the text, or after you read the text, or as you're reading the text. And you can also actively watch these videos by having a notebook handy or having a notes, maybe Notability open while you're watching the video to start jotting down some questions you might have. So chemistry is the study of matter, and matter, of course, is anything that has mass and takes up space. So a few examples of matter would be things like atoms, maybe molecules of an element, maybe molecules of a compound, or then mixtures of all of these possibilities. So an element that exists as an isolated atom at room temperature would be something like helium or neon or argon, the noble gases. Many of the nonmetal elements exist as molecules at room temperature. So things like hydrogen, nitrogen, oxygen, these exist as molecules of H2, N2, or O2. Now, elements can get together and rearrange their bonding so that they bond with each other, where we get compounds. Compounds are where we have two or more elements chemically bonded together. So things like water, H2O, or methane, CH4 would be examples of molecules of a compound or molecular compounds. Then lastly, we can have mixtures of all these different types of matter mixed together. And of course, we can even have more complicated types of matter, like macromolecules, things like proteins, very large molecules that we'll discuss later in Chapter 12, or you'll address later in courses such as biochemistry or organic chemistry. We can describe matter as being a solid, liquid, or a gas. I think what's important for us to recognize at this point, in the solid phase, we'd have intermolecular forces holding our molecules together. If we break some of those forces, then the molecules can then tumble about each other, but we still have a fair amount of attraction between adjacent molecules in the liquid phase. Then if we heat up a liquid sample, eventually it boils, and then we have isolated molecules in the gas phase that no longer have any attraction for each other. We'll describe the nature of gases in Chapter 10, the nature of liquids in Chapter 11, and solids the next chapter in Chapter 12. Now we can classify a given piece of matter based upon its composition. So if you follow the scheme, you can determine how to classify any type of matter. So the first question you would have is the sample uniform throughout? If you look at the sample, does it all look the same to the naked eye? If it does, then that would be what we call homogeneous. Now, if you can distinctly see two different phases, like you're looking at an orange wedge, so you can clearly see the flesh of the orange, which kind of looks uniform. I mean, maybe you can see some of the flesh versus some of the water separate from each other, and can clearly see a mixture there, but also you have the peel, which clearly means we have a heterogeneous mixture. You might imagine a salad dressing that's settled, like an oil and vinegar type problem, where you can see the oil layer and the vinegar layer. That's definitely what we'd call a heterogeneous mixture. And so that would look not the same throughout, but if matter looks the same throughout, you may not know if a given piece of metal may look very shiny, it may look homogeneous, but you may not know if it's a pure substance or some type of mixture. Usually you have a tough time answering the next question. Does the matter have a variable composition? The issue here would be a little bit more about things you may know about the matter. Can you break it apart into different substances? Did you take two substances, mix them together, and then later you can get back to the same two substances? If that's the case, then we're not really dealing with a pure substance. Rather, we have just a mixture. We're just taking two different substances and mixing them together. If the material does not have a variable composition, the kind of chemistry question would be, do you have two distinct different types of compounds or molecules present, or do you have just one type present? If you have just one type present, then you would say, aha, we have a pure substance. And so if you have a pure substance, it means all the molecules are of the same type, of the same molecule, but it may not even be a molecule at all. It may just be an element. So the next question would be, does the sample, does the matter contain more than one kind of atom? Like, are there two different types of elements present or just one? And again, you can just generally answer this question by looking at the sample. Maybe you'd have to do some type of test on the matter to see if it does contain more than one atom or not. Can you break the sample apart into smaller components is sometimes a question, because maybe you can take H2O, water, and separate it into hydrogen and oxygen, two smaller elements, or two smaller elements compared to the size of the molecule. So if it contains only one kind of atom, then we'd have an element. If it contains two or more kinds of atoms, two more different elements, we classify that sample as a compound. So the purpose of this slide is to talk a little bit more about the classification of matter based on composition. Of course, atoms are the building blocks of matter. Each element is made of a unique kind of atom, but can be made of more than one atom of that kind. We'll talk about isotopes when we get into chapter 2. So we'll see that, for example, carbon exists naturally about 99% of the time, where it has 6 protons and 6 neutrons in its nucleus. And the 6 protons is really what separates carbon from nitrogen. Nitrogen has 7 protons in its nucleus. But the number of neutrons sometimes is variable. So carbon also exists about 1% of the time with an extra neutron. So with 7 neutrons and still the 6 protons. So it has one extra neutral particle, but the same number of positive particles. And we'll talk all about that in chapter 2 in case you've forgotten how to count protons and neutrons for a given atom. But now a compound is made when atoms of 2 or more elements combine to form chemical bonds. So we have things like water and ethanol are molecules of the compounds water and ethanol. And then we have O2, oxygen, is the molecule of the element oxygen. And so a molecule of oxygen is not a compound because it only contains one element. Carbon dioxide, of course, is a compound. Ethylene glycol is a compound. Ethylene glycol kind of looks like ethanol. Ethanol has an OH group on 2 carbon atoms that are saturated with hydrogen. We'll talk a little bit about how that works in chapter 2. OChem kind of picks up more on the chemistry of organic compounds, but ethylene glycol just has that extra OH group, kind of an OH group on both of the carbon atoms in the compound. Then they give the structure of aspirin here. This model here, these are like what we call space-filling models, kind of just showing how the atoms are kind of overlapping to make compounds. There are a couple of laws and things like the law of definite composition, or sometimes called the law of constant composition. Sounds really complicated, but this is a really simple idea that says if you have a water sample, that every single water molecule has 2 hydrogens and an oxygen. And if you have like an oxygen gas sample, that all the atoms are O2, or all of the sample exists as O2 molecules. And if you have hydrogen, it's all H2. And so the idea here is that the law is saying that our compounds have this definite composition, that either it's all oxygen molecules in the case of O2, all H2 molecules in the case of hydrogen, or all H2O molecules in the case of water. So 2 hydrogens for every 1 oxygen. And you get that each and every time for the molecules within the sample. So we talked earlier about classifying mixtures. Mixtures exhibit properties of the substances that make them up. Mixtures can have a variable composition throughout the sample. That's heterogeneous. This is what we can usually see with our eyes. We can usually see multiple layers, like within a piece of granite, where we can see the different colors. So we know definitely granite would be a heterogeneous mixture. We can also then see other samples, like we have here a sample, looks like a chemical, but it's certainly homogeneous. If you look at the powder here, you may not know if that's a homogeneous mixture or if it's just a pure substance. Turns out that's probably copper sulfate, and it's probably pure, or we assume is pure. Like when I say pure copper sulfate, maybe you may say, well, certainly there's got to be some kind of impurity in the sample. So whenever I say, or generally it's said that we have a pure substance, we're talking, 98% pure sample would be mostly copper sulfate. Then whenever you mix it with something, say you throw it into water and it mixes, and you get yourself a homogeneous aqueous mixture. An aqueous mixture is just one where you're dissolving the substance in the water. That's a topic for chapter 4, where we talk about all different kinds of aqueous chemistry, but homogeneous mixture is something we often call a solution. The text introduces 2 different terms, intensive properties and extensive properties. An intensive property is one that's independent of the amount of substance that is present. These are important properties because they really are characteristic of the substance. So things like the density of a substance, the boiling point of a substance, the color of a substance. These are all things that help us identify and really characterize a given substance. An extensive property is a property that depends on the amount of the substance that's present. So this is usually just things that indicate how much of the substance you have, like the mass, the volume, or the total energy, the total amount of heat that a substance has, for example, or things that aren't really so much classifying something characteristic about the property, but just something indicative of how much of the sample that is present. We also see two different types of changes that are mentioned. We have a physical change versus a chemical change, and it's really important that we understand the difference. A physical change are changes in matter that do not change the composition of a substance. When we have water boiling, we're not breaking bonds between water molecules. We're not breaking the OH bonds between the oxygen and hydrogen atoms. Rather, we're breaking the intermolecular forces that hold two water molecules together. So when we boil water, we're going from having H2O molecules interacting with each other to then having H2O molecules far separated from each other. So we're breaking the individual molecular attractions when we boil a substance. We're not changing or breaking the chemical bonds. A chemical change implies that we're making new substances. So maybe we take water and oxygen and figure out how to get them to react together to make hydrogen peroxide, in which case we end up with a new compound. Maybe we do this through things like combustion reactions, oxidation reactions, decomposition reactions. We'll talk about some examples of these types of reactions in chapter 3. But the key would be a chemical change is giving us new substances. Whereas a physical change is just simply changing like the phase or the physical characteristics of a solution, like going from a solid to a liquid to a gas, but still within the exact same molecule, versus breaking and changing chemical bonds and actually coming up with new reactants, or new products from breaking the bonds or rearranging the bonds in our reactants. So this slide here is just giving us a reminder that when we go from solid to liquid to water vapor, that we're just going from having H2O molecules frozen in space relative to each other, tumbling about each other, or far separated from each other, but still 2 H's for every 1 O in each molecule within molecules of water. Now there's some discussion. I think these are really just to describe some different ways you might understand separating mixtures, so we can understand how you might separate the components of a mixture. The 3 key methods that we'll see are filtration, distillation, and chromatography. And we'll give some examples on the next slides. So filtration is probably the most obvious method for separating the components of the mixture. So if you had a solid substance that's mixed with a liquid, just use some filter paper. This is really easily done in a chemistry lab. Also really easily done with a coffee pot. Distillation is a type of way of separating mixtures utilizing or taking advantage of differences in boiling points. So if you imagine having a salt water mixture, you have NaCl, the boiling point of sodium chloride is really, really high. But the boiling point of water is relatively low. So if you boil a mixture of salt water, you're going to have a higher composition of water that makes it into the vapor phase. And so then if you condense those vapors, you're going to get mostly pure water condensing into your distillate. So you can imagine taking advantage of a distillation step. Anytime you have a liquid that has another liquid or another substance in the mixture with it that has a different boiling point. Chromatography is another technique for separating mixtures. This probably has been done most often whenever you're using a pen and you get your water wet that you're using the pen on, and then all of a sudden you see like a black ink pen actually has multiple different dyes within it, usually like a purple and a bluish color, and you can see those colors eluting through the paper as the water makes its way through the paper. And what you're seeing in that example would be that the ink molecules travel through water. They have like a different affinity for the paper as the water is flowing through them, so you see the colors emerge in your paper as your ink's kind of disappearing or sort of being removed in this process from where it was originally. So this technique, you can use this in the lab. It's not one that we really use a lot in general chemistry, so this will probably be the only time in this slide that you ever see this technique. But the idea is if you take something like paper or like silica gel, something that's kind of sticky, and then you take a mixture and flow through it, then the different molecules have like a different stickiness through that solid phase. And so then you can separate your mixture into its components just by them having a what's called a different retention time, or a different amount of time it takes them to flow through that solid support. So now maybe you fill this with something like alumina, something like sand, something like a silica gel, just something that's a solid material that the molecules in your sample are sticking to at different rates and then flowing through the sample with a different amount of time it takes them to reach through and flow through that device. One of the changes with the 14th edition of the textbook that we're using from the 13th edition and earlier versions of the textbook is there never used to be this discussion of energy at this stage of the textbook. But I think it's good that we talk a little bit about energy to define what it is, what it means. When we start saying energy, what do we mean? Well, having energy means you have the capacity to do work or to transfer heat. So if a substance has a lot of energy, it means it can heat things up or it can push things around. So work is the energy transferred when a force is exerted onto an object and then displaces that object, puts it into motion. So it takes work to put things into motion. And then heat is the energy used to increase the temperature of an object. So you combust natural gas, so you can use the heat generated that's being given off by the methane molecules forming CO2 and water as they combust. So energy is being lost. You see that in the form of the flame if you're using a stove. And then that heat then can be used to heat something up like a pot of water. And so then we can also separate the idea of force with, force is the push or pull on an object. And so that kind of relates back to work, that work is going to be the force applied onto an object to move it some distance. So work is kind of the energy associated with putting things into motion. Heat is the sort of property associated with the temperature of an object. It's important, I think, that we differentiate the two different forms of energy. We have kinetic energy, the energy of motion, and potential energy, the object just kind of, as it relates to where an object is relative to where it could be. And then what I'd like to do is kind of take us from the big to the small, from the sort of real world to the chemical world type example here. So we have an example here of a bicyclist at the top of the hill. They would have a high potential energy. They would have the high potential to lose energy, to lose that potential energy by going down the hill, and gain kinetic energy in the process. So the bicyclist originally begins, say, not moving at all, so they have zero kinetic energy. So if you're not moving, you have no kinetic energy. And then all of a sudden you're going down the hill, you've picked up some velocity, you have mass, 1/2 mv squared gives you the kinetic energy. Now we can think of kinetic energy of anything. You can think of a baseball, a bicyclist, anything with mass, anything where you can characterize the velocity, you can calculate the kinetic energy of that particle or of that substance, whatever it is. Then if you then say, well, what about potential energy? If I'm thinking of a reaction, maybe we can start thinking about the potential energy of the differences of bond energy. So let's start thinking about something like CH4 plus O2. Natural gas combusts. Give this a flame and then you spontaneously will get CO2 and water forming very rapidly. So if we balance this, not that the balancing matters, we talk about that in chapter 3, but we just have a balanced reaction of a gaseous CH4 molecule reacting with gaseous O2 forms CO2. That's a gas at room temperature. And water could be a liquid at room temperature, but when you're combusting a natural gas sample, you would probably not see like a rain cloud above this. You probably see steam and sort of the flame emerging from the burning of the natural gas. And so this is kind of like a bicyclist scenario here, but with the molecules, where we start with a high potential energy with our CH4, then we end up forming our CO2 and water that are now more stable. They have now a lower potential energy from where we began with our CH4 and our O2. So now, just as a consequence of what we know about this reaction, we know this reaction takes place with a flame. We know that's a lot of heat being given off. That heat being given off is the kinetic energy being given to those molecules, like flying away from the reaction as it takes place, if you will. It's the bicyclist going down the hill. It's the CH4 and the O2 losing potential energy, making the more stable bonds in CO2 and water. Now, you could have a lot of questions. You could wonder, well, why are the bonds more stable? That's a question for later. We'll talk about bond enthalpies in Chapter 5 and Chapter 8. And we'll start learning how to characterize reactions in heat in Chapters 3 and in Chapters 5. And we'll start learning how to name different types of compounds and just going through some different classifications of compounds in the next chapter, in Chapter 2. So my plan for lecture videos is to wrap them up with a couple examples towards the end. We have this just one page of examples for this introduction to the first half of Chapter 1. So first example will be white gold contains gold in a white metal such as palladium. A sample of white gold is uniform throughout. Classify white gold as an element, compound, pure substance, homogeneous mixture, heterogeneous mixture. Well, the fact that it says that the sample is uniform throughout says it's homogeneous. Okay, so we know we're homogeneous. And so then we might wonder, when we have our sample, do we still have gold and palladium just mixed together? And from what this example says, that sounds like it's the case. It's not as if gold and palladium are now bonding with each other in some kind of new way, making some type of gold-palladium compound. It's really just a case where we have homogeneous mixture. Okay, so we could tell it's homogeneous just because it's uniform throughout, and then just from the nature of what we're told, and that we're not told that the gold and the palladium are somehow reacting with each other, that they're just mixing throughout in a uniform fashion. So we have a homogeneous mixture for this problem here. A homogeneous mixture of two different elements. Now that's different. You take hydrogen and oxygen and take them together and then light them on, you can actually make a flame, just hold a flame to it and it goes kaboom. A huge reaction takes place. You know, given the reaction that you can hear with your ears, we'll do this in class, you will see the reaction take place with your own eyes. You know a reaction occurred. Then that's where you say, okay, now we've made H2O. Or we've at least made a new compound from those two different elements. Much different than just mixing two metals, nothing goes kaboom, no bonds change. You can get the metals back again later if you were to separate them afterwards. Okay, next question. Classify a grapefruit as, so I'm picturing here a whole, unpeeled grapefruit. So classify a grapefruit as an element, compound, pure substance, homogeneous mixture, heterogeneous mixture. Clearly this is a heterogeneous mixture. So this is just a simple example of having more than one type of substance present. And we can clearly see that with our eyes. So we know we have a heterogeneous mixture. So give an example of a substance found in grapefruit. Well, probably the most obvious substance present in a grapefruit would be water. Another substance we're going to find in grapefruit's likely going to be sucrose, some sort of a sugar. We're likely going to find citric acid. And of course, we're going to find a variety of other compounds and other types of macromolecules within a grapefruit, but those are some obvious candidates for compounds that we just can be fairly certain from our knowledge of nutrition that can be found in a grapefruit. So clearly a mixture, and clearly by inspecting the grapefruit, a heterogeneous mixture. So this concludes our pre-lecture video for the first half of Chapter 1. If you're looking for more content, I recommend reading over sections 1.4 through 1.1 through 1.4, or looking for some of the problems in the textbook, either the sample and practice exercises or some of the end of chapter problems. The practice exercise and some of the end of chapter problems are answered in the back of the textbook as well, so you can check your work as you attempt some of those problems. Thank you for the attention.